In this presentation, we are going to discuss about scheduling algorithms. So the outlines are basic concept, CPU scheduler, scheduling criteria, scheduling algorithms, thread scheduling. So the basic concept is maximum CPU utilization obtained with multiprogramming. CPU I/O burst cycle process executions consist of a cycle of CPU executions and I/O wait. The CPU burst followed by I/O burst. CPU burst distributions is of main concern. CPU scheduler. CPU scheduler selects from among the processes in ready queue and allocates a CPU core to one of them. Queue may be ordered in various ways. CPU scheduling decisions may take place when a process switches from one running to waiting state, switches from running to ready state, switches from waiting to ready state, and terminates. When scheduling task plays only under circumference 1 and 4, the scheduling scheme is non-primitive, otherwise it is primitive. Scheduling criteria. CPU utilization keeps the CPU as busy as possible. So the throughput is a process that complete their executions per the unit time. Turnaround time, amount of time to execute a particular process. Then the waiting time, the amount of time a process has been waiting in the ready queue. Then the response time, the amount of time required or takes from when a request was submitted until the first response is produced. Scheduling algorithm are maximize the CPU utilizations, maximize the throughput, minimize the turnaround time, minimize the waiting time, and also minimize the response time. The first algorithm is first come first serve scheduling. So here consider the process and its burst times are P1 24 and P2 has 3, P3 has 3. Suppose that the process arrive in the order of P1, P2, P3. The Gantt chart for the schedule is first P1 is executed, it has burst time is 24. After that the P2 is executed, then the P3 is executed. So its executions is done with the upcoming service. So the wait time for the P1 is 0, the waiting time for the P2 is 24 and the P3 is 27. The average waiting time is 17. So in this, suppose that the process arrive in the order. Here, suppose the process arrive in order P2, P3, P1. The Gantt chart for the schedule is initially P2 is executed, afterwards P3, then P1. So waiting time to be changed. So for the P1 is 6, P2 is 0, P3 is 3. So the average waiting time is also 3. So much better than the previous case. So the next scheduling is shortest job first scheduling. Associate with each process the length of its next CPU burst. Use this length to schedule the program with the shortest time. So SJF is optimal. Give minimum average waiting time for a given set of process. Primitive versions called a shortest remaining time first. How do we determine the length of the next CPU burst? Could ask the user and estimate. The example, consider the three processes P1, P2, P3. Each has the burst time 687. So in this scheduling chart, first the P4 is executed, then P1, then P3 and P2. So its average waiting time is 7. So here the process is executed based on the burst time which has the low value. So here the P4 is the low, so first executed. Afterwards in this order, P1 is next executed, then P3, finally P2. So how to determine the length of the next CPU burst? So can only estimate the length. So should be similar to the previous one. Then pick the process with the shortest predicted next CPU burst. Can be done by using the length of previous CPU burst using the exponential average. Then shortest remaining time first scheduling. Primitive versions of SJN. Whenever a new process arrives in the ready queue, the decisions on which process to schedule next are done using the SJN algorithms. So an SRT more optimal than the SJN in terms of the minimum average waiting time for a given set of process. So the example, consider four process P1, P2, P3, P4 with the arrival time is 0, 1, 2, 3, 4. The burst time is 8, 4, 9, 5. So its Gantt chart is the first process P1 is executed, then P2, next P4 is executed, then P1 is executed, finally P3 is executed. Next one is round robin algorithm. Each process gets a small unit of CPU time, usually 10 to 100 milliseconds. After this time has elapsed, the process is permitted and added to the end of the ready queue. If there are n processes in the ready queue and the time quantum is q, then each process gets 1 by n of the CPU times in chunks of at most q time units at once. No process waits more than n minus q time units. The timer interrupts every quantum to schedule next process. The performance is q large is an first in first out. Then the smallest round robin. So note that q must be large with respect to context switch, otherwise overhead is too high. So the example, consider three processes P1, P2, P3. So the Gantt chart is, it has the time quantum is 4. So first the P1 is executed the first 4 burst time. Afterwards the P2 execute, then P3. The remaining part of the P1 burst to be executed. This time quantum and context switch time. Then priority scheduling. A priority number is associated with each process. The CPU is allocated to the process with the highest priority. So it is a primitive or non-primitive. So SJF is the priority scheduling, while the priority is the inverse of predictive next CPU burst time. So example, in the priority scheduling, the process, consider P1, P2, P3, P4, P5, 5 processes are going to execute. So here the burst time is 10, 1, 2, 1, 5. Then the priority is 3, 1, 4, 5, 2. So here the first priority for the process 2. So first one, the first execution is done for the process P2. The next priority is P5. So next P5 is executed. The next priority is, third one is P1, then P3, then P4. So here it has the average waiting time is 8.2. So when we compare Priority scheduling with the round robin, run the process with the highest priority. So process with the same priority run round robin. So that to be explained. So with the example, the 5 process and its burst time with the priority. So based on the priority, the process are executed in the round robin. And in the priority scheduling is very important here. Then multi-level queue. The ready queue consists of In the multi-level queue, the ready queue consists of multiple queues. Multi-level queue scheduler defined by the following parameters: number of queues, scheduling algorithms for each queue, methods used to determine which queue a process will enter when the process needs service, scheduling among the queues. So in this multi-level queues, with the priority scheduling have separate queue for each priority. They schedule the process in the highest priority queue. The thread scheduling distinguishes between the user level and kernel level threads. When the threads supports the thread schedule, not process. Many to one and many to many models thread library schedules user level threads to run the LWP, that's known as the process contention scope. The multiple processor scheduling. CPU scheduling is more complex when multiple CPUs are available. So multi-process may be any one of the following architectures: multi-core CPUs, multi-thread cores, NUMA systems, heterogeneous multiprocessing. So in this multiple processor scheduling, it is what with the common ready queue and the per core run queue. So in this multi-core processor, recent trends to place multiple processors core on same physical chip is a faster and consumes less power. Multiple threads per core also growing. Takes advantages of many share to make progress on another threads while the memory retrieve happens. So in this multi-threaded multi-core systems, each core has greater than of one hardware threads. So if one thread has a memory share, switch to the another thread. So real-time CPU scheduling. So it had the two types: the interrupt latching, dispatch latching. So the time from arrive of interrupt to start the routine that service interrupt. So the time for schedule to take current process of CPU and switch to another is in dispatch latency. Priority based scheduling, where the scheduling is done based on the priority of the process that is to be executed the particular periodic time. So the time essential, that is an time scheduling is an important. So the rate monotonic scheduling. A priority is assigned based on the inverse of its period. So shortest periods higher priority, longest periods lower priority. So which have the executions is shortest period, so that is to be executed first. So which has the highest priority. The earliest deadline first scheduling. So priorities are assigned according to deadlines. The earlier the deadlines, the higher the priority. The later of the deadline, the lower of the priority. Okay, thank you.